strict when it satisfies this condition, then this implies that the trace of a first quantized Hamiltonian must actually have been 0. And so we can forget about this. And then we also realize that since H is Hermitian, so it's traceless, H transpose is the same as H star because it's Hermitian, and therefore this condition is actually nothing else but H star being equal to minus H up to some possible unitary rotation, which comes from this unitary matrix that appears in the definition of charge conjugation. So that's the condition that this charge conjugation invariance implies on the first quantized Hamiltonian. You should notice that it's very similar to time reversal. So time reversal meant that H star is equal to plus H up to some unitary rotation. Charge conjugation means that H star is equal to minus H up to some unitary rotation.
Could you repeat why trace H implies that that's 0?
I think we just do the exercise. It's simple, right? So it's you just have to, if you evaluate the trace of this equation, you see that there is already traces here which multiply the identity matrix. So there's a factor of n. N is the dimension of a matrix appearing here, and there's some other traces that appear here. And unless n is exactly equal to 2, which we're not interested in because n should be large, we're interested in thermodynamic limit, this will imply trace H is 0. Yeah, I can also do that. Well, see, here it's actually 0, so it's just a fact, right?
It doesn't have to be 0 just by this identity.
That's what I'm saying. So that was the other person's question. So this identity implies that trace is 0, right?
And also minor comments that you mean many bodies on the right hand side of H hat.
Yeah, there's a typo. Yeah. Thanks.
Is it fair to say that charge conjugation at the second quantized level is unitary, but if you write it into the Fox
Indeed. So that's kind of confusing. So let me write this down in the box here. And so time reversal, and charge conjugation in second quantized and in first quantized language, which it mean what means, so this means that when the corresponding operators act on the Hilbert space of second quantization, which is a Fock space, or on the Hilbert space of first quantization, which is just the n-dimensional space of single particle states. So time reversal is anti-unitary, and it's anti-unitary also in first quantization, but charge conjugation is unitary in a second quantization, but anti-unitary in first quantization. And so I'll spell this out right away in more detail, but it's obvious because there's a star, but we can spell it out more clearly. So this is this board here. So as we did for time reversal, we can introduce a convenient notation, if we like, to say that if we let the second quantized version of the operator only act on the first quantized Hilbert space, then we give that operator some other name, It's no new operator, it's just convenient to write in this way. And so then this condition here, which is equivalent to saying that the first quantized Hamiltonian, which is just a matrix, is satisfies this property, which is the same as this property, if I'm willing to declare C, it's a thing that acts on a first quantized Hilbert space, single particle Hilbert space, is complex conjugation times a unitary matrix, which is just the unitary matrix we had introduced on the top. All right. So then this K part of the definition of C makes the complex conjugate here, and the rest is the same equation. Okay?
Although even that's confusing because you have K on both sides somehow. I guess K only has to divide.
No. So UC K H, and then we take the inverse. This is K inverse, UC inverse, which is UC dagger. And K squares to +1. If I conjugate twice, I get nothing. So that means K inverse is K. Right? And so UC K, if I like. But by definition, what K does, it just complex conjugates all the matrix elements. So it's the same equation. Okay? Yeah? All right. More questions? Yes? 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 Yes. So the statement I made the last time about modding out by all the symmetry operation that commute with the Hamiltonian, all the symmetry operations of a system that are realized by unitary operators. So the statement I made, when we read it carefully, was always that this was on the first quantized Hilbert space. So all these statements were in a first quantized Hilbert space. And so it's consistent with precisely this, that charge conjugation is also anti-unitary when it acts on the first quantized Hilbert space. So it's something we have to consider in the process of modding out. So we cannot mod out by these. Okay. Other questions? Yeah.
Does it make sense to classify non-completely?
Okay, yeah, we haven't done that, yeah. So the question is, it makes sense, I guess. You have to just argue with yourself or the colleagues, what physics problems are part of that discussion, right? Which physics problems you want to discuss that way. So, well, the question was, so we've always looked at unitary systems, if I understand correctly, unitary Hermitian Hamiltonians. And the question is, what if we do generalize the problem to non-Hermitian Hamiltonians? And of course, we can think about that. But before we do that and invest a lot of time, we should think about what physics problems we address that way, right? Right. So indeed, it hasn't been done. Yeah. Yeah. Okay. So for now, as we have, there's a good question. So right now, we've only discussed second quantized Hamiltonians, which have charge which conserve the particle number. So these are non-superconducting systems. And later in today's lecture, I'll just remind ourselves as a simple exercise that the entire formalism can be taken over to discuss also Bogoliubov-Duchenne Hamiltonians. with the condition that every Bogoliubdjian Hamiltonian is just one of these, which has however, it has an automatic charge conjugation symmetry, turns out, which you probably know if you know something about Bogoliubdjian Hamiltonians. And so everything I say now can be instantly transposed to include also Bogoliubdjian Hamiltonians, even though the formalism I've written it so far in does not yet discuss that issue. All right. Other questions? All right. So we have now the anti-unitary charge conjugation, and we can play the same games that we played before with time reversal. So we can ask, what if I apply charge conjugation twice? So then this is of course a unitary operator, so it's some kind of unitary operator, and it's described by some unitary operator, and that unitary operator acting on fermion creation operators in the way we defined the last time. That unitary operator is characterized by some matrix U, and by a matrix U. So C squared can be characterized by some matrix U. The question is, what is that matrix? And it's an exercise which is very simple, which I repeat in a slightly different language below. It's similar to time reversal. It's UC star, where UC is this unitary operator appearing in the definition of charge conjugation. And so if you want, we can prove this easily by just using this definition here of charge conjugation. So in the first quantized language, so if I apply the first quantized charge conjugation operator twice, it's UCK, but K is K inverse. So it's UC, K, UC, K inverse. This, by definition of what K does, gives the complex conjugate matrix. And so charge conjugation is described, when you square it, by unitary operator, which is characterized by precisely that matrix. Right? And then, just as for time reversal, we can, so if you have a system that is invariant under charge conjugation, it's also invariant under charge conjugation squared. And this is equivalent in first quantized lingo to just saying that this UC U star operator, UC star, commutes with H, first quantized Hamiltonian. All right. And just as, let me write it on this board. So then we have an operator, unit operator, this one. It commutes with the first quantized Hamiltonian, and as for time reversal, where we had the same type of condition, we conclude that the eigenvalues of, so UC star must be a multiple of identity, and it can be either plus or minus the identity, so that c squared is just plus or minus 1. So this mimics precisely what we discussed for time reversal. And so the conclusion is there are three ways A Hamiltonian, and here I'm talking about non-interacting fermion systems, so we talk about the first quantized Hamiltonian. That's the Hamiltonian that characterizes non-interacting fermions. So the Hamiltonian can respond to a charge conjugation symmetry well, c squared is plus or minus 1, and in some notation we just denote that symbol c squared, which takes on three values, plus 1, minus 1. And if you have a system that is not invariant in a charge conjugation symmetry, we write a 0 there. That's the definition of what the symbol means, c squared or c. So it's obvious H is charge conjugation invariant, and c squares to plus 1. H is charge conjugation invariant, c squares to minus 1. H is not charge conjugation invariant. So there are three ways. Mimics exactly the discussion we had for time reversal. Finally, questions? Finally, we should note, in analogy to the discussion we had for time reversal, when the first quantized charge conjugation operator squares to minus 1, that implies, so it's a unitary operator, c squared, described by this UC star. And that unitary operator defines the definition on creation and annihilation operators, which are precisely characterized by this UC star. It's only minus 1, so not much happens. So obviously, it will be this. So if I apply, in this case, the charge conjugation operator twice on a fermion annihilation operator, I get a minus sign. And similarly, if I apply it twice on the creation operator, I get a minus sign. And then again, since every state in the Fock space is created from the Fock space vacuum by applying some number of creation operators to it, the action of c squared on the Fock space is graded by fermion number. And so where, as before, Q is the number operator in second quantization, thing that counts how many fermions we have, and this operator is the fermion number parity operator as before. All right? So maybe it's useful to think about in slight more detail about the action of charge conjugation defined in this way, which maybe I don't erase it. I write what I want in the equation below. So what does this operator do? charge conjugation on the fermion-Fock space. It does the thing that we think it should do. Let me write it down. So the fermion-Fock space is graded, meaning it's just a sum of Hilbert spaces. There is one for each particle number q, where q is the eigenvalue of a number operator. And so q is the eigenvalue of that number operator. And so now, maybe it's obvious. So charge conjugation acts so that it maps any state of a Fock space that contains q fermions into a state of the Fock space that contains n minus q fermions. Remember what n was? N was the number of latticytes the system had, or if there's Pauli spin, twice the number of latticytes. So n is the dimension of a single particle Hilbert space, and so that's what this operator does. And in particular, it maps the state which is spanned by the vacuum. So this is a state. The Hilbert space is one-dimensional. It has just the Fock ground state, a Fock vacuum, and it gets mapped into the. So it's a completely empty state. It gets mapped in the completely filled state, and the completely filled state is the eigenstate. There's only one state that spans Fn, Fock space with n particles, as many particles that can be accommodated, and that's the state, completely filled state, where you filled all the single particle states. Right? And also when n is an even integer, which it often is, then f of n over 2 is mapped into n over 2. So half filling gets mapped into half filling as expected. So that's what this operator does. So I'm not divulging any secrets. It's obvious. Hang on. Yeah.
Can any of this formalism apply to bosons?
Well, yeah, so that's a good question. So it is not useful, right, as it's written for bosons, and nobody has really successfully translated in anything having to do with bosons. That's, of course, related to the fact that a boson system without interaction is a very fragile system, because as soon as you induce any infinitesimal amount of interaction, the system likes to do other things like Bose condensation, right? So it's not a physically useful notion to talk about a non-interacting boson system.
So yesterday, when you talk about time reversal operator, it also squares to fermion curve.
Yes.
Minus 1.
Indeed.
Is there any deep connection for this and that?
Well, the argument is just that it's the same argument. That's the connection if you want. There's no further deeper connection. It's so right.
We're always discussing squaring plus or minus 1. What about something to the fourth power higher? Those things.
Well, if you square it once more, then it squares to plus 1.
I mean something to the fourth power being minus 1.
Yeah, well, these things don't do that. Yeah, but not in this language of non-interacting particles that we're discussing now, right? Yeah. So what you're really asking is that you have some kind of projective representation of these objects, right? So then things don't square really to +1 or -1, but maybe some other root of unity, some phase. But we're not discussing that here.
Since time reversal, previous reversal, and charge conjugation both square to parity. I always
Yeah.
which is
No, well, we derived it. It's true. It's just a fact of life. Yeah. So maybe that doesn't contain too much information, right? That's something these two operators square to fermion parity. Okay, that's it.
Can you remind us again why for a single fermion z square and equal to -1?
Well, it's the same argument we had for time reversal. So it arises from this condition. Where is it? Is it still on the board? This one. So there's an operator that commutes with a Hamiltonian, and that's a unitary operator, right? So unitary operator can have eigenvalues only which are phases, right? And then you have to make that argument we made for time reversal symmetry. So one argument is a physical argument that if you apply charge conjugation twice, you expect you get the same ket up to possibly a phase, right? And then the phase can be determined by figuring out, by doing this. UC star, UC, you can bracket it this way and can bracket it this way. The two must be the same by associativity or matrix multiplication, and then you get ±1, right? So the other argument is that ultimately the Hamiltonians is not one Hamiltonian, but it's a whole set of Hamiltonians, and they span some kind of algebra, complete algebra, reducible algebra, and then something that commutes with this must be by Schur's lemma a multiple of the identity.
Stupid question, but what I was asking is why -1 not +1?
Well, there are two options, just as for time reversal symmetries. Think about time reversal symmetry. Why is there a -1 possible? Well, that's Kramer's degenerate and all this, right? So there's an analog of this. Right. More questions? Yeah?
Starting from the definition, how do we see the theorem?
How do we see what?
See that theorem, the mapping from
Well, so if imagine C is defined that way, right? And then imagine what implications it has on the creation operator. So maybe I should do this exercise. Let's see. Maybe that's useful to have. So let me show. So one way of thinking is that this action of charge conjugation on the Fock space is your fundamental way of thinking about charge conjugation. And as I said, if I have a half-filled state when Q is n/2, n being an even integer, it maps the half-filled state into itself. And so what I'd like to do is to think about in this way. So if I can first apply C, first apply a creation operator and then C, or first apply C and then a destruction operator, which is sort of what this equation means. And I can check. So if I take FQ and apply first a creation operator, then I raise the particle number, and then under charge conjugation, it goes into n minus q plus 1. And if I do this, I first start with fq, and then apply first charge conjugation, and then apply the destruction operator. I get f n minus q minus 1, which is the same. So that illustrates that this definition is consistent with this definition on the creation and relation operator. Maybe that's useful to think about. And if you think about it in some other way, so we can also ask, what does charge conjugation do to the number operator? Q is this. And so that's an exercise. So maybe you should do that. It's a simple exercise. And we use the definition how C acts on creation relation operators, and a simple line, one line calculation tells me that this is n minus q hat. So all these things, I think, should convince you that the two things are exactly complementary. Okay? Questions? So, in other words, another way of thinking about it is if you define the operator. So, if n is even, and then you define delta q is q minus n over 2. N over 2 is half filling. Then this means that C hat delta q, C is minus delta q, right? So it's exactly what you think that particles go into holes with respect to half filling. Right? Yeah.
Shouldn't charge when C squared is equal to minus 1, shouldn't charge conjugation also enforce some sort of degeneracy?
Yeah, we can talk about this. So everything that we know follows from this. Yeah. All right. So now there's a last item which we need to discuss. So I'm going very slowly. I'm sort of building things up from scratch. So now we have T and C. And maybe you might think that we should discuss the composition of T and C, which in a Fock space is a unitary operator. Is an anti-unitary operator. So, and the first quantization is a unitary operator. And that is something that is maybe not so well known. It's a chiral or sublattice symmetry. None of the words are important. They're all historical because people have discussed the symmetry in various special examples, which are systems that are, quote, chiral or have, quote, some sublattice symmetry. But the general notion is independent of all this. And we define the operator S, which is time reversal, composed with George conjugation symmetry. So that's the definition. And so I will now try to explain why we should care about this object. And first of all, since we have already the definition of T and C on the creation relation operators, we know how this acts on creation relation operators. And let me just summarize that statement. So this is already known. There's nothing to be discussed. It follows from what we already said. So since charge conjugation maps creation into a relation operator and backwards, S must do the same because time reversal doesn't. So because time reversal in Fock space is unitary, charge is not anti-unitary, this is unitary, second quantization. This is also an anti-unitary operator in Fock space. And that's the definition. And now the last question we have to answer is, what is the matrix U? It's of course determined by the matrices that appear in time reversal and charge conjugation. And if you do the exercise figuring out U for S is UT UC star. Okay.
What does that say?
Which?
Equals to minus I, S times what?
S, oh, so there's a typo probably, yeah. Identity matrix. Thanks. So then we can have a Hamiltonian in second quantization. So that is invariant. H invariant under this S symmetry. So that means that S, H, S inverse is H, that's invariance. And that means, so it's an exercise by just translating into first quantization, US H, first quantized Hamiltonian, U as dagger is minus H. And it also implies if S is a symmetry, then trace H automatically will be 0 because it's similar to charge conjugation. It maps psi's into psi daggers and psi daggers into psi. And so this one we can easily remember by just thinking about the first quantized implementation of S on a first quantized Hilbert space. Let me do that now. Yeah.
At the level of second quantized Hamiltonian, you always have that.
Yeah.
It's not the common.
Indeed. Right.
So
It's
true for T as well.
it's true for all operators. Right. So the only difference where it looks different when you actually look down at the level of the first quantized Hamiltonian, then more structure appears. And so again, as we've done before, if we take the second quantized version of this operator and think about the first quantized variant, first quantized version, so we let it act only on single particle states in the Fock space, then it's some other operator, let's call it S. But since this S operator is just the product of time reversal and charge conjugation. It's the product of the single particle versions of time reversal and charge conjugations, for which we had already discussed. So time reversal was complex conjugation times some unitary matrix. Charge conjugation was complex conjugation left multiplied with some unitary matrix. And then, of course, K is K inverse. And so we learn that this is UT, K, UC, K inverse, but that's just another name for the complex conjugate matrix. So it's UT, UC star, which is exactly what I've noted above. And so now, so now one thing okay, so that's it. And so S is just, we have just introduced an extra symbol for something we already defined. So S is just the product of the two unitary matrices UT and UC star coming from time reversal and charge conjugation symmetry. And so this here, so if S is a symmetry, then it's an operator that anti-commutes with the first quantized Hamiltonian. So that's the important thing to remember. So if this S is a symmetry, then it's a peculiar symmetry. It's not what we usually call a symmetry in quantum mechanics, of first quantized quantum mechanics. It's an operator that anti-commutes with the first quantized Hamiltonian. Right? Okay. Questions? So let's now work out a little more detail about this S, because it turns out S is an important ingredient. So while S is of course unitary in first quantization, it's a product of two anti-unitary operators in first quantization. It's not something we usually call a symmetry. And so therefore, it's not something we would have modded out right away when we mod it out by all the unitarily realized symmetries. And so I'll come back to that shortly.
And why is the charge conjugation I? That just comes from the.
Yeah, so we just defined it that way. We're free to define it, right? Because we have just defined it in the equation I've just erased on equation relation operators. I haven't told you what happens if it acts on I times equation relation operator, right? So we are free to do whatever we want, and we define charge conjugation by being a unitary operator in Fock space. Maybe that's not that bad, because you might worry that where is the other version, which is anti-unitary. But that version is just that other operator, because once we switch behind charge conjugation, the time reversal operator, which is anti-unitary operator in Fock space, we get something that basically looks like an anti-unitary version of what was on the other board. So which one we want to call which is up to us, right? But we have both available, right? As I said, this is pure historical. When people discuss that in a history of a subject, people realized that this is a symmetry of some Dirac Hamiltonians, which were chiral in some sense, in a Dirac sense. And then people realized that this symmetry, which has this property, is realized in simple models of hopping Hamiltonians and bipartite lattices, which have a sublattice symmetry. And these people called it sublattice, but people didn't really, at that time, see the bigger connection, that this is just an abstract object which is nothing else but the product of time reversal and charge conjugation symmetry. We don't have to think about any detailed realization of that. Right? Yeah? I can't hear you. Indeed. I will come back to it. It's a very good question. Very good question. Yeah, it will be on the next board. Yeah. All right. Yeah, I will come back. So the reason why we need to worry about this is is the statement I glibly made, which is this minus sign here, or this minus sign. So S is not, if we think about the big picture I outlined the last time, we try to mod out by all unitarily realized symmetries on a single particle Hilbert space. Right? So this one isn't gonna get rid of by modding out. We're not gonna get rid of this because it's not what we usually call a symmetry of the first quantized Hamiltonian. So we somehow need to handle it, keep it. And so I'll say.
Well, I guess I don't know if that's just comment on what I meant.
Oh, okay.
If it's a composite of two symmetries, so you principally know everything about it.
That's right, but think about it the following way. So imagine you have a Hamiltonian that is not invariant under T, and it's not invariant under C, but it's invariant under this. So you need this notion independently. Right? And there are Hamiltonians we care about. One appeared in Ashwin's lecture yesterday, A3. A3 is one of these. It's not invariant under time reversal, not invariant under charge conjugation, is invariant under this, S, turns out.
If that's true, why don't you define S in a way that does not rely on P and C? I think you define it.
Yeah, but I want all of them, because as we will see, all of them will give rise to the whole table, and we need to understand all of them at the same time.
I mean, if I just take a definition of S, I just remove TC, and I have all these relations. None of them.
Oh yeah. Maybe I don't need to know that S is a product of T and C. I don't need to know that. I can just define it. But it's probably useful to know we can do something, simplify calculations by knowing that S is a product of T and C.
In those cases when there's symmetry.
Yeah, okay. If we have an S and a T symmetry, then we know already what S does, basically, right? So we don't have to do extra calculations. We know the result already. So that's the benefit of having that relationship, right? All right. Let me. Yes, it turns out. Yeah, I haven't proven that, but yes. Right, it will come from things I'll say later about T and C. Because there's only one T and one C, which is basically this complex conjugation times a suitable matrix, and which matrix I choose that I can change. So, and S is just a product of these two. I understand what you're saying, but it's true, but I haven't really proven it, but it's true.
I guess I'm just going to ask, is this special case of interest when tau and C are not symmetry,
Yeah.
S is a symmetry, is it that each of them anti-commutes with the Hamiltonian, but then tau and S commute with the Hamiltonian?
No, S will anti-commute with a Hamiltonian, which is this, and there's no other relationships.
No, I meant with the many-body. So
Oh yeah.
S commutes with the many-body Hamiltonian, but tau and C anti-commute with the many-body. Then the minus sign.
so in the many-body Hamiltonians always have this structure, as we discussed earlier, right?
Symmetry.
But it's a symmetry.
Right, but then let's say tau and c anti-commute with a many-body Hamiltonian.
In first quantization. No. So the second quantized state.
No. Suppose you have a case where tau and c are not symmetries of the many-body Hamiltonian.
Oh,
But they anti-commute. They're not a symmetry of the many-body Hamiltonian. They anti-commute. Then that minus sign will cancel when you construct that.
yeah,
Is
but
that the case?
yeah, I don't think it's useful to consider this, or we don't usually.
I'm just thinking that minus.
Yeah. So if we had the wrong definition, so if you have a Hamiltonian that looks like this in first quantization, then so you have a minus sign here, right? Then you always want to say the words that H is invariant under charge conjugation symmetry. Right? So, and whenever you have this, H is plus H, U diagonally with a different U, then you always want to declare this as going with the words saying your Hamiltonian has a time reversal symmetry, right? And whenever you have a Hamiltonian that has this property, U double primed dagger is minus H, you always want this to go with the words the Hamiltonian has this chiral symmetry, right? All right. So now we can again look at the square of S, and the square of S will of course commute. So the square of S will commute. And so again, S squared. So we know already what S is, but we know what S squared is. It's US squared. Remember with US, U is UT, UC star. So because it commutes with all these Hamiltonians, it again will be a multiple of the identity. And the factor must be a phase because these are unitary matrices. And then we just have to remember that US is really UT and UC star. Now, we can use the freedom to redefine UT by an arbitrary phase. And US, UC, by an arbitrary phase. That's so because whatever we have derived about time reversal and charge conjugation never dependent on that phase choice. We can pick any choice, and none of what we've derived will depend on it. None of what we've derived about time reversal and charge conjugation symmetry depends on that, because remember, there's always a UT star appearing UC star, which are plus or minus 1. And none of it depends on these phases. So make a choice we can make a phase choice such that that phase is 0. And when we made that choice, S squared is just 1. Which means that S dagger is S inverse is S. Okay? So that's up to us, and we will make that choice, that phase choice. It's a good choice to make. It simplifies life. And then S squared or US squared is 1. And so whatever we'll do now, we'll make the arguments we will make them with this phase choice. Okay, now, so I'm done with the S symmetry, chiral symmetry, and I'm coming back now to the question that was asked. So there's an alternative definition of S, which is as good as the one we had before. Namely, we could say S is really the other order of C and T. Let's call it S primed. So we go over there, it's just the other order. And so we haven't talked about what S and T do, where they commute or what they do, so we don't know. So we have to consider this. And then, again, it's convenient to introduce the first quantized version of this. So it's the second quantized operator acting on the first quantized Hilbert space alone. And so we know what this is. It's C times T as opposed to T times C. And we can of course, work this out. So it's UC, complex conjugation, UT, complex conjugation, and it's UC, UT star. And so we may want to call that U, how do I call it? US primed. So now it turns out that life is simple. So we want to compare this S primed or US primed with this S or US. And so now so there's a question, you know, S and S primed, what do they have to do with each other? But this is simple. So simple because, okay, S is TC, UT, UC star, S primed is CT, UC, UT star. So let's take this equation and take the adjoint. S dagger is UC star dagger, UT dagger. So this is obviously UC transposed UT star transposed. So now let's make a side calculation exercise on this board. So now we use elementary facts about charge conjugation and time reversal on their own. So time reversal T is UTK, and then T squared is something proportional to the identity, but it's a sign. So epsilon of T is plus or minus 1. So then we know that UT star is precisely that sign. So if we multiply both sides of equation with UT star dagger, we find that UT is epsilon T UT star dagger, which is epsilon T UT transposed, which means that UT transposed is epsilon T times UT. So we probably know this. UT is a symmetric matrix when T squared is plus 1. UT is an antisymmetric matrix when T squared is minus 1. So that's what it tells us. And we can repeat the same calculation for charge conjugation. C is UCK. C squared is epsilon C 1, where epsilon C is a sign. And for the same reason we had for time reversal, we conclude that UC transposed is epsilon C UC, which means that UC is symmetric when C squared is plus 1. UC is antisymmetric when C squared is minus 1. And so that's the key to this here. So now we know that we can get rid of a transpose by potentially introducing two signs. But UC, UT transposed is just the other S. But now we know from the conventions, which I erased, that S and S squares to 1. Therefore, S dagger is S, and so we learn that S is epsilon C, epsilon T, S primed. So we learn that C and T commute or anti-commute depending on the product of the two signs we get for time reversal squared and charge conjugation squared. So that means that the two matrices or the two operators are always the same up to a sign. So it doesn't matter which order we choose. All right. So that means also that because this goes over into the second quantized operators. All right, so that's the answer to your question. Good. Well, it depends on, it's just what time reversal and charge conjugation square to, right? So remember, so let's go back to that definition, to that discussion. So the C squared and S squared are fermion parity only if the corresponding C or S operator is squared to -1. So the statement was that T squared is -1, then in second quantization, but if T squared is +1, then, well, T squared in second quantization is plus the identity. So C squared is -1, and then C squared is -1 fermion parity. But if C squared is +1, then the square of C squared is just +1, right? So, and this signs plus or minus is this epsilon. So this is epsilon T. So here, epsilon T. This is epsilon C, and this is epsilon C, right? So that's a statement. Yeah?
Whether C square or T squares is equal to plus or minus 1.
It depends on model. So we have 10 cases, and it depends on which of the 10 cases we look at.
T squared equals -1. Think of it as a fundamental property of fermion having spin 1/2.
Well, not necessarily. It's much more general because you may have fermions that have some other property, right? They transform in some group, and some representation of a group have the minus sign, like the spin 1/2 of SE2, and others don't. So it's a very general statement, right? It's beyond spin 1/2 or Pauli spin, right? So that's the advantage of this. This doesn't make any assumption about anything. It's just complete. It's just quantum mechanics, doesn't it? All right. Question?
Does it change anything if we shift Q by 1?
Well, I guess we can just rewrite Q as Q prime plus 1, and you get corresponding formulas. I'm not exactly sure what.
So if we, so it seems like the way we derive it is from the action of the sign. For example, where it's like C, the -2 is minus sign.
Yeah, so C squared or T squared is -1 to the Q. And Q just counts the number of fermions. And it's defined with respect to the fermion Fock space. So the vacuum in Fock space has Q equals 0. And so how many fermions you add to the vacuum, you change the sign, right? So that's the definition. Well, yeah, the vacuum is the Fock vacuum, I guess, right? So you could discuss the other vacuum, meaning the completely filled state, where all the fermion orbitals, all the fermion levels are filled. There's a completely filled state, and you can discuss that as your Fock space, which means you exchange fermion creation relation operators. So whatever fermion you create on the empty vacuum, you have to destroy from the top vacuum these corresponding, right? And when n is odd, there's a change of q goes to q minus 1 under this particle hole exchange, right? So that would realize what you want, I guess. All right. So I'm running late, very late, but so let me do this. So far we've just outlined convenient notions, convenient definitions, and we've discussed what they mean. And so the next statement is a statement that goes back to the first lecture, where we try to mod out by the unitarily realized symmetries on the single particle Hilbert space. So that statement that I'll make now is kind of simple, but it's important. So it turns out we need to consider only one T, one time reversal, and one charge conjugation operator. So we think about them now on first quantized Hilbert space and the anti-unity operators, and those are the ones we don't mod out. And so these are the ones we have to deal with. And you may ask, well, what if I have two time reversal operators? You know, what do I do? So what does this mean? So I claim it doesn't happen. So assume there were two time reversal operators. So let's give them some name. So T1 and T2. They are both complex conjugation. And of course, the only thing they can differ by is by having different matrices. And now we know that when the t is squared to plus 1, the matrices must be symmetric. T squared minus 1, the matrices have to be antisymmetric. And then so then let's look at the composition. So T1 times T2, we can also choose the other order if you like, is UT1 K, UT2 K, so this kind of argument we had many times before. So it's a unitary operator, and which unitary operator is given by the two unitaries for T1 and T2. So that's unitary. So, but also, what we can of course do is we can write T2, okay, which is UT2 times K. We can finesse it in a form that brings in T1. So obviously we write T1 as UT1K, which is precisely T1. And then this is T2. and then we have to fix this. Okay, and okay, so this is some matrix, some unitary, and so then we learn very simple, obviously, the innocent calculation. So T2 is the same as T1 up to some unitary. And so let's now go back to think about this logic. So we mod out by all unitarily realized symmetry operation of a group G0. And then once we've taken care of these unitarily realized symmetries, we have to look at the blocks. And the blocks don't know anymore about the symmetry. And so now, if we had another time reversal symmetry, so maybe we have to add this other symmetry to G0, and then we get a bigger group, G0 primed. It could, of course, also happen, if we had two time reversal operators, that this unitary symmetry is already part of the group G0, and we don't have to do that. But in either case, we go back to the original situation that potentially we have a larger group of unitarily realized symmetries, and maybe we have to reorganize the blocks. But then we have only one time reversal symmetry, because adding the other time reversal symmetry doesn't change anything, right? So adding another time reversal symmetry, the only thing that can do is potentially enlarge the symmetry group of unitarily realized symmetries. And then once we have that larger group, once we have T1, we also have T2. It's nothing new because U was already in a symmetry group. So we don't. So we really have only one T, and we phrase in this way as saying that modulo unitary symmetries. So it means what I just said. If we had another T, then that other T can be accommodated by just enlarging the symmetry group. And as we know, the structure of the blocks does not care, as I mentioned the last time, what the symmetry group actually is. And so we can do the same thing for C. Not time reversal, but charge conjugation. The same argument applies if you had two charge conjugation symmetries. You make the product, but one charge conjugation isn't really any different from the other one. Potentially, you may have to enlarge the symmetry group, but that doesn't cost us anything. So the only trouble now is, so now you may think, well, what about this S? S is also a unitary object, but so can we do the same thing with S? So can I dispose? Let's imagine I discuss only time reversal symmetry. And then is it possible to dispose of the anti-unitary charge conjugation symmetry by doing something similar, by just looking at the product? So, but we cannot dispose in the sense of, say, C while keeping T because S, which is TC, which is unitary. Well, it's unitary is okay, but it doesn't commute with H. So we cannot declare that the difference between S and T, or S and T inverse, is just can be accommodated for by enlarging the unitarily realized symmetry, so G to G naught, G naught to G naught prime, by adding S, because S is not what we call a symmetry of the first quantized Hamiltonian, because it is a minus sign. It's not what we call symmetry. So therefore, we have to somehow keep S in a loop. We have to keep discussing S, and that's what we'll do now. Questions?
Do you see you get a T1 and T2 commute with every element?
No, I'm saying that if I have some, so I'm looking at symmetries. So there's two types of symmetries: the unitarily realized symmetries, and those that are not unitary, anti-unitary symmetries. And now I say, imagine I have two anti-unitary symmetries, T1 and T2. But I've just shown that if I have those, then the two differ by just a unitary, right? But of course, so the whole group of unitary and unitary symmetry, also you can compose them. It's also a group, right? So once I have the anti-unitary and the unitaries, I can multiply them together. And that's what I'm doing here, right? And so all I'm saying is that two anti-unitary time reversal symmetries differ only by a unitary realized symmetry, which I've already been discussing and I've modded out by, right? So if I want to discuss the question, which I want, what do I get when I discuss, in addition to the unitarily realized symmetry, what I get new when I discuss the anti-unitary realized symmetries? In that process, I need to discuss only one time reversal symmetry, because any other time reversal symmetry is just that one I have already kept times some unitary stuff that I've modded out. That's the logic.
That's not the logic, but are we guaranteed it forms a group?
Yes, we can check. Yeah, we can check. Right. Okay. Good. Yeah?
Sorry, asking this question this late in the game, but how do you define anti-unitary?
Yeah.
But then I'm confused why you define C inverse equal to I. So I asked this question before.
Let me, so let's see. So anti-unitary, so these are symmetry operations, so these are operators on the Hilbert space, right? And so operators can be linear operators. And the unitary versions, norm-preserving ones, are those that are unitary, right? But then I have anti-linear maps, right? So that it changes the coefficient of complex conjugates. And if they preserve the norm squared, then they're called anti-unitary. So the anti-unitary ones are really antilinear. So if I have an antilinear operator, the anti-unitary one being a special case of that, and I have A1 plus B2, then so they would be A star A1 plus B star A2. So that's an antilinear,
That's what
right?
I thought. But then how is it consistent with, for C, for charge conjugation, you define C inverse as equal to plus I?
That's in the second quantized formulation. So that
I is a number. In what sense is it
they're different.
well,
So that's not obvious, but that comes.
the numbers?
What?
Even when they act just on numbers?
Well, so C dagger, I, C inverse.
But if you change the C dagger and C, is that different? And then you get
So when I translate the property that a Hamiltonian is invariant in second quantization under C, when I translate this in the first quantized language, I buy a transposed in the Hamiltonian, in the first quantized Hamiltonian. But since the Hamiltonian is a Hermitian operator, is a Hermitian matrix, the transposed is also a complex conjugate. So I can think of the corresponding H star UC dagger is -1. So that is the same. That's the same statement for non-interacting second quantized Hamiltonian. The minus sign comes from fermion, but there is a transposed or a star, and I can interpret this as being K inverse.
Here you mean plus I.
Sorry, I meant plus I. Sorry, sometimes there are typos. Yeah. So, but when it acts on this Hamiltonian, there's a complex conjugate, right? And that's why in first quantized language I can think of charge conjugation as an anti-unitary operator. So that's all there is.
Yeah, so that part I understand. I just, the first statement, consistency of the first statement with the last statement.
Yeah, so then we have to do this exercise to show that this is equal to that. Right? And so then this can be written as C inverse is minus H, defining C as UCK. So this is the same as this, just a formal way of writing it, right? And since K acts is complex conjugation, it's anti-unitary, right? So it's kind of peculiar, but so that's a convenient. See, maybe we don't have to do it that way. If you're willing to discuss an operator, see, if you're willing to write H transposed here, we are as good as before, right? So then you have to just think, what does it mean that you have a transposed? So how do you think about this in first quantized Hilbert space? It's less convenient, right? Because you have to switch bras and kets and so on, right? So this is more convenient to think about.
Oh, I see. That star comes from not complex conjugation. It comes
From transposed, because
I alone, but it's just transposed. But
Yeah.
by hermeticity,
Yeah.
it gives
Yeah.
you a star.
Yeah.
And so really, it is leaving I alone.
Yeah. All right. So I'm minus 7 minutes over time. Is that right? What? Yeah. Okay.
Maybe a good time to break for a thought.
Okay. Yeah, so the next time I will use this to do topological stuff with. So far, we've done sort of just quantum mechanics. Yeah.
So when we decompose our space into the unitaries, so we do this block diagonalization, why can we be sure that the anti-unitaries don't kind of mix the blocks?
Yeah, they do, and